Good morning, everyone. Today, we're excited to present our final project on gold price forecasting with Bayesian vector autoregression. This project is part of our course, Seminar 298, and we're Group 6. I'm Yipeng Huang, and this is my teammate, Ruiqi Mao. So let's start with this quick question. If I ask you to predict the price of gold 3 months from now, given the historical data from the past year, how would you approach it? Would you expect the price to go up or down? Would you base your prediction on market trends, economic news, or maybe historical data from other precious metals like silver? You might be thinking, we don't have enough data for an accurate prediction. So here, we've gathered some relevant data sets. We're looking at not just gold price, but also related financial indicators like silver futures, exchange rates, and market trends. Additionally, I have blurred out data beyond the January 2025 to simulate a real-world forecasting challenge. But what if these different data sources contradict each other? Central bank policies, geopolitical conflicts, and inflation expectation all impacts gold prices. Yet they do in complex and sometimes conflicting ways. How do we quantify these factors effectively? Simply relying on past trends may not be enough. Are you ready to rethink the way we make predictions? Let's dive into how Bayesian vector autoregression help us tackle this challenge. Now that we've introduced the challenge of forecasting gold price, let's make a closer look at the model we're using in this project, the BVAR, Bayesian vector autoregression. The equation shown here represents the mathematical structure of a BVAR model, which is an extension of the standard VAR model, but with Bayesian priors applied to its parameters. So the YT here represents a vector of all the variables we're analyzing at a given time. And the C here is a constant term and represents the baseline level of each variable when all lag effects are zero. In simpler terms, if there were no changes in past values, this term would still contribute to the current prediction. And the AI here is the lag coefficient matrices. And AI matrices contain coefficients that define how past values influence the present. And for P, this is the number of lags. This represents how many past time periods are included in the model. A higher P means that the model considers a larger historical trend, while a smaller P makes it more responsive to relevant or to recent trends. And the epsilon T, this is the error term, accounts for randomness and unknown factors. For example, if the stock price suddenly crashed due to unexpected news, this will show up in epsilon T. And you can see it, the epsilon T follows the normal distribution with mean zero and covariance matrix sigma, which captures the interdependence between different variables errors. Let's break it down. So the BVAR is a flexible framework that can incorporate new variables and impose conditions for alternative economic projections. It also has a forecasting performance comparable to that of CBO's baseline forecasting method. I'll give two questions and answer them. So first one is, why is VAR, the vector autoregression? Why we use that is because VAR models multiple time series by capture the relationships between variables over time. It allows each variable to depend on its own past values and the past values of other variables, enabling dynamic interactions. And another question here is, why is B, the Bayesian method? So the BVR differs with standard VR model in that the model parameters are treated as random variables with prior probabilities rather than fixed values. This is very suitable as a model for gold price prediction because the weight of the factors affecting gold prices are not constant. But how is it compared to each other in forecasting models, let's put them in this table. From the table and row to row, the first question is, does this model captures time dependencies? The linear regression, of course not. It only models the static relationships. For the VAR and BVAR, both of them is yes, because they use lag values allowing the model to capture historical patterns and dynamic interactions between variables. The second question here is there any risk of overfitting? For the linear regression, of course, the risk is low because it uses fewer parameters and you assume the situation are linear. And for the VAR, it's relatively high because VAR freely estimates all parameters using only historical data. If the data set is small, it will overfit by capturing noise instead of real trends. And for the BVAR, it's relatively low because it introduced Bayesian priors, which acts as a form of regularization. This prevents the model from overfitting by smoothing parameter estimates. The last question here is, does it work well with small data? Of course, the linear regression, because it requires few parameters and quite intuitive. And for VAR, it does not. It needs a larger data set because each lag introduces more parameters, making it unreliable with small data set. But for BVAR, the answer is yes, because Bayesian priors help stabilize the estimates, allowing it to work even when the data set is small. If it's still not very intuitive, let's go deeper firstly with an example. Imagine you're running an ice cream shop in a tourist destination. You want to predict how many ice cream you'll sell tomorrow. What factors would you consider? Most likely, you look at two things, the temperature and the number of tourists in town. So, in the linear regression ways, this is a simple approach. You might say, if it's hotter, people buy more ice cream. But what if there's a heat wave and it's too hot? Sales might actually decrease. And what if the number of tourists also matters? Linear regression assumes a fixed relationship, which is too simple. Things are always coupled together, not independent, as what we learned in class. When you're trying to use the VAR, it improves this by considering how past values affects current values. So if yesterday was not hot and tourists' number was low, we might expect the sales would also be weak today, and vice versa. However, VAR has a major weakness. It relies only on data. If we have a small data set, it overfits, meaning it mistakenly picks up random patterns instead of real trends. Like currently, LA is raining and sunny, and you can't predict tomorrow's weather by only based on today's weather, right? And when it comes to BVAR model explanation, I would say that let's add it into our consideration. And the BVAR brings in prior knowledge. For example, we might assume that long-term trends matters more than sudden changes. Instead of letting the model overfit every small fluctuation, BVAR smooth the prediction, ensuring that sudden spikes in the temperature don't lead to unrealistic forecasts. So come to our conclusion of this example. Why we use BVAR? Because it gives us the flexibility of VAR, but with the better stability. It works even when data is limited, just like how a shop owner uses both past experience and real-time data to make business decisions. And that's exactly why BVAR is used in financial market, economic forecasting, and even government policy planning. Let's nextly come to some applications of BVAR. So Bayesian vector autoregression is a powerful statistical tool widely used for analyzing multivariate time series data. BVAR's flexibility and ability to incorporate prior information make it suitable for forecasting, policy evaluation, and scenario analysis across diverse fields. Its applications extend beyond economics and finance to energy, health, and social science. In the following blocks, you can see that they can be used in macroeconomic forecasting, financial market analysis, climate and environmental economics, supply chain and operations management, and even urban and regional studies. So far, we've discussed the broader application of BVAR, which should give you a qualitative understanding of its properties and strength. Now, shifting back to our specific research task, my teammate will take over to dive deeper into our data selection, model setup, and final results part.
Now I'm going to introduce the data selection of our Bayesian model. The data for this study were sourced from the investing.com website, covering the period from March 4th, 2020 to February 28th, 2025. To simplify the model, the closing price of each variable were ultimately chosen as the variable for model construction. The specific variables included the following 5 variables. First is gold price against US dollar. Second is gold price against euro. Third is silver price against US dollar. And the fourth is SP 500 index. 5 is the exchange trade from fund price, which is expressed as ETF. The price of the gold against euro and against the US dollar are closely related, as both are derived from the same global gold market, and fluctuations in one usually reflect in the other due to arbitrage opportunities. And the gold and silver are often moved together due to their shared status, because metals and and the self-haven assets. However, there's some difference between these two prices. Gold tends to react more strongly to microeconomy factors like inflections, insurgencies, and geopolitical risks. And silver price is more sensitive to industrial demand because it's broader used in manufacturing and technology. So the silver price are generally more volatile than gold price. So the relationship may vary depends on market conditions. SP 500 index, the relationship between gold is totally different from we introduced before, because gold is often considered as a safe haven asset, while SP 500 represents the risks on assets. Typically, when SP 500 declines, the price of gold is driving up, and when the SP 500 raises, the price of gold may decline. And the price of the ETF, which is exchange traded fund, such as SPDR Gold shares, which allows investors to buy into gold without buying mining stocks, are now major gold buyers and sellers. Many ETFs track the price of gold directly, so changes in the price of gold in USD are reflected in this ETF. Both ETFs trade on the exchange like stock and measure the holdings in ounces of gold. Still, these ETFs are designed to reflect the price of gold, not moving it. And now we can see the model of a VAR model with P lags, where P is the number of lags and Y is variables. For example, the price of gold in USD or in euro, etc. And the system can be expressed as the equation below, where YT is the vector of variables at time t. We have introduced these variables in the slide before, and the AI is the coefficient matrix for lag I. UT is multivariate Gaussian noise with zero mean and covariance matrix sigma. In Bayesian autoregression model, prior distributions are placed on the model parallels, which is AI and sigma. The AI is priors on coefficient matrix. The prior distributions are typically Gaussian, which is shown here. And AI0 is the prior mean of AI, which often, for example, often a shrinkage towards zero for the regularization. And the omega I is the prior covariance matrix, which controls the uncertainty of AI. And the sigma is the prior on the covariance matrix. The covariance matrix is typically given an inverse Wishart prior, which is shown here. S is the scale matrix, which determines the spread of the prior distributions. And V is the degree of freedom, which controls the concentration of the prior. And now we come to the most important part of our model, the likelihood set and posterior distributions and the forecasting mechanisms. The likelihood functions for observation is shown here as like a multi Gaussian distributions, and the posterior distributions combines the likelihood and the priors. Is shown here, and where PYAI sigma is the likelihood of the data, and PAI is the prior on the coefficients, and P sigma is the prior on the covariance matrix. For forecasting, we give the estimated posterior distribution of AI and sigma. We can then forecasts are made by iteratively applying the model with these equations, where H is the forecast horizon, H is the predicted steps, how many days we are going to H. We predict H days ahead data, and then the initial values for predictions are taken from the most recent observed data. We are going to do this equation again and again until we finish all the prediction of the test data set. And in summary, there are three key parameters of our model. The first is the time lag P, which is the number of past observations used to predict the future values. And the second is the prior sightings, which will control the regularization and the shrinkage of AI and sigma. And the third is the forecast horizon H, which determines the number of steps into the future for prediction. And here is how I set up the model in MATLAB. I use this function BASVARM in MATLAB to set up the BVAR model, and these are the 5 variables, and the effective sample size is 1,220. The number of equations are 5. Number of estimated particles are 105. Here is the innovations covariance matrix of the 5 variables. Now we are going to the prediction result of the God price. We use 4 indexes to evaluate the performance of our Bayesian VAR model. I'm going to introduce them in the following slides. And the forecast horizon H is set as 2, and the time lag P is set as 4. Back to the prediction results as shown in the figure here. The blue line represents the real God price against US dollar, and the red line represents the predicted price. The red area represents the 95 confidence interval. From the figure, we can see that the predicted God price is close to the actual price, and the trend is basically the same. The actual God price is generally within the confidence interval predicted by the model. Now I'm going to combine these four indicators to quantitatively evaluate the predictive ability of our Bayesian BER model. The first is mean absolute error, which is represented as MAE. This is the average of the absolute differences between the predicted value and the actual values. On average, the model's prediction are off by 19 units of the XAU divided US price. Low MAE value indicates the better accuracy of the model prediction. And the mean absolute percentage error, which is represented as MAPE, is 0.71%. This represents the average percentage error between the predicted and actual values. And this number indicates the model's predictions are on average within 0.71% of the actual gold price. Lower MAPE value suggests a higher accuracy. And the root mean square error, which represents as RMSE, is about 26. This matrix parallels the larger error more heavily than MAE, as the errors are squared before averaging. And RMSE of 26 means that the model's prediction deviated on average by about 26 units, which with large errors being given more weight. Low RMSE values indicate better accuracy. And the last but not the least is the coefficients of determinations, which is R square, is equals to 0.9485. This means the matrix explains the proportion of the variance in the actual values yi that is captured by the model. An R square value of 0.9485 means that there are 94% of the variations in the actual gold price against USD dollar is explained by the model's prediction. And R square close to 1 indicates a strong predictive ability. From the residual distribution histogram and the fitting curve on the left here, we can see that the residual distribution is close to normal distribution, and the mu of normal distribution is approximately equals to 0. This shows that the model has no obvious deviation in prediction error. The lower left figure here shows the residential time series. We can see that the residuals are redundantly distributed and fluctuated around the zero line, and indicates that the model has no systematic deviation. The autocorrelation on the figure on the right here is, we can see that there is no significant lag correlation in the ACF graph. Only the first lag is higher than the coefficient confidence interval. This indicates that the model can basically capture the relevant information in the time series. Now let's look at two important variables which affect the predictive ability of the model. The lag is the number of past time periods used as input variables in the model to predict future values. For example, if lag is 4, the model considers data from the previous 4 days data to make predictions. This helps the model to understand how past values influence current and future values, accounting for temporal dependencies. Higher lag values increase the complexity of the model and allows it to capture more intricate relationships. But the trade-off is choosing too many lags can lead to overfitting or inefficient use of resources. However, if we choose too few lags, this can lead underfitting, which will miss important historical dependencies. and the h is the step size of the model prediction. For example, if h equals to 2, the model predicts the gold price for the next 2 days based on the available historical data. This defines how far into the future the model's prediction extended. Shorter intervals are generally more accurate, while longer intervals introduce more uncertainties. Large prediction intervals increase the difficulties of maintaining accuracy because errors can accurate over time. Based on this, it's not difficult to explain that the difference in model prediction accuracy caused by these combinations of data variables. From data, we can see that the smaller h is and the larger lag is, the more accurate and the model prediction is. We use rolling window cross-validation to verify the reliability of the model training. First, we divide the data into multiple training sets and the test sets. For each validation, we use a part of the data for training, then use the next gold price data for testing, and the record of evaluation indicators, MAE, RMSE, etc. for each time. Since the period of gold is time series, the rolling window moves from the front to back in time order. Each test set is followed by the training set. And here are the MAE, RMSE, MAPE, and R square value of all 57 folders during the cross-validation progress. The average value of each evaluation indicators is represented by a red dotted line in these figures. For the model behavior, we can evaluate from two aspects: overfitting, underfitting, and the stability. For overfitting and underfitting, the similarity of average matrix between training and testing datasets indicates that the model does not exhibit significant overfitting and underfitting. It performs consistently across both datasets, all these datasets. And for stability, the notable fluctuations in performance for folder 15 to folder 57 highlights the potential instability in the model. This may be due to some abnormal data in certain sections of the gold price series. Validation variability in cross-validation matrix suggests the model may not adapt that well to some subsets of the dataset, raising concerns about its robustness. Overall, this project demonstrates the effectiveness of the Bayesian vector autoregression model in forecasting the general trend of gold futures price over 2 months period. The high accuracy of this model is attributed to its proficient ability to capture the intricate relationships among variables and to analyze market dynamics. And there are some limitations and future works I'm going to talk about. The study's limitations include the use of limited data, which in this model is 2020 and to 2025, and also about the potential oversight of some influential variables like other precious metals and crude oil types. To improve, future works should consider a broader range of variables and longer time series data. Additionally, integrating advanced prediction methods like machine learning algorithms could also enhance the accuracy of the model. Furthermore, improving the model's sensitivity to small price changes is also very crucial, but maybe some difficult to do. And here are the references paper we read to set up the model and also to get further understanding of the Bayesian model.